and welcome back to Back Row Tutoring. In this video we're going to be looking at resolving forces in Newton's laws, and this is video number 2 of 6 for our forces topic, so let's get right into it. Resolving forces is like the opposite of finding the resultant force. You are trying to find the horizontal and vertical components of one force. This just means you're trying to split one force into two forces acting in different directions. Resolving forces is really very easy. Let's say you have this force here, which is 400 newtons in this direction. You need to draw on the vertical and the horizontal. Let's call this x and y, where x is across the page and y is up and down the page. Once you've done this, draw lines at the end of the force, connecting it up to your dotted lines. And once you've done this, draw in your vertical and horizontal components. This is just two arrows which go to where the lines that you've just drawn went to on the axes. Now measure the original force and work out a scale. Work out what 1 centimetre represents. So, if we take a ruler and measure this 400 Newton force, we can see that it's 7 centimetres. 400 newtons divided by 7 represents 57.14 newtons per centimetre. So that means every centimetre represents 57.14 newtons. We now need to make a note of this and remember it for later. Now you need to measure your components. So using your scale, you can work out the force in each direction. The vertical is 3.1 centimetres and the horizontal is 6.1 centimetres. 3.1 multiplied by our scale means that our vertical, or this arrow here, represents 177.13 newtons. 6.1 multiplied by our scale, because we had 6.1 centimetres here, well, that represents 348.5 newtons. So we'll have 348.5 newtons in the horizontal. And that's all there is to it. Practice makes perfect with resolving forces. So firstly, come up with a scale by measuring the first force. Once you've measured the first force, you need to draw lines into each of the axes, so the horizontal and the vertical axes. And then you need to measure the horizontal and the vertical and then multiply it by your scale to get the to get the components in the x and y direction. If you're following along in your revision workbook, complete task number 6 and pause the video now. So, forces cause things to happen. When a force is applied to an object, it can cause changes in an object's motion. These changes are modelled through Newton's laws. Newton has 3 laws, each of which describes what happens to objects when forces are applied in different ways. Let's have a look at Newton's first law of motion. Newton's first law of motion states that if the resultant force on an object is 0 and the object is stationary, then the object remains stationary. If the resultant force on an object is 0 and the object is in motion, then the object will continue to move at a constant velocity. So that's quite long-winded and complicated, so let's simplify that a little bit. This basically means that if an object has no resultant force, then it will experience no change in velocity, where velocity is just speed in a certain direction. So if the object is already moving and there is no resultant force, it will continue to move at that speed. If the object is not moving and there is no resultant force, then it will continue to stay still. We say the object is stationary. If a car is moving to the right and these are the forces, what will happen? It will continue to move to the right at 3 meters per second. And that's because we have 400 newtons acting to the right, 400 newtons acting to the left. That means there is no overall resultant force. And because it was already travelling to the right at 3 meters per second, then it will continue to move to the right at 3 meters per second because there is no resultant force. If a skydiver is falling at 10 meters per second, and these are the forces, what will happen? Well, let's have a look. It will continue to move down at 10 meters per second. So because the parachute was moving down, or the parachuter, or the skydiver I should say, was moving down at 10 meters per second, and there is no overall force, there is no resultant force, then the skydiver will continue to move at a constant velocity at 10 meters per second. So when a vehicle travels at a steady speed, the resistive force balances the driving force. This is because when it is travelling at a steady speed, where there is no change in speed, the forces are balanced and there is no resultant force. So, Newton's first law states that if something is moving at some velocity, it will continue to move at that velocity if there are no external forces acting on it. If an object is stationary and there are no overall forces acting on it, then it will continue to stay stationary. So what happens if there is a resultant force on an object and it is not in equilibrium? If there is a resultant force, then the object will experience a change in speed. So remember, no resultant force, no change in speed, even if the object is already moving. If the car is moving to the right and these are the forces, what will happen? Bearing in mind this time we'll have a larger force to the right. It will experience a change in speed, as taught in Newton's second law. The tendency of objects to continue in their state of rest or of uniform motion is called inertia. Again, that's quite long-winded and complicated. This just means that when an object is still, inertia is the name given to the property which keeps that object still. Or, if it is moving, it is the name given to the property that keeps that object moving. So if you have something which is moving already, inertia is just the tendency for that object to continue moving with the absence of external forces. If you're following along in your revision workbook, pause the video now and complete task number 7. We're now going to have a look at Newton's second law of motion. Newton's second law of motion states that the acceleration of an object is proportional to the resultant force acting on the object and inversely proportional to the mass of the object. That basically means that objects which do experience a resultant force will have acceleration. Acceleration is a change in velocity, so objects which have a resultant force will experience a change in speed, or another way of saying a change in speed is saying that they accelerate. Let's go back to that car travelling at 3 meters per second to the right. The resultant force here is 400 newtons to the right, and that's because 800 subtract 400 is 400 newtons. What do you think will happen? If you said it will accelerate to the right, then you are correct. This is because there is a resultant force causing a change in velocity or an acceleration. So, because there is a resultant force to the right here of 400 newtons, there is a change in velocity, because where you have external forces or where you have resultant forces, the speed will change. But there's more than that. Newton's second law tells you that objects accelerate, but it also comes with a formula. So it tells you the rate at which it accelerates. Acceleration is a vector, so it has a direction. It's the same direction as the resultant force. And this is the formula which comes with Newton's second law. F equals ma. Force is equal to mass multiplied by acceleration. The second formula that you need to know from forces is F is equal to ma. This is heavily linked to Newton's second law, and this is actually one of the most important formulas in the whole of physics. If you go on to study this further, if you go on to A-level, or if you go and do a degree or something like that, this comes up over and over again. Force equals mass times acceleration. But what actually is acceleration? Acceleration is just the change in the speed of something. If acceleration is positive, then the object is speeding up. If the acceleration is negative, then the object is slowing down. This is also known as deceleration. The units for acceleration are meters per second, or m/s/s. Or meters per second squared, or m/s squared. Let's have a look at a work example. A car is travelling down a road and has 300 newtons of driving force and 150 newtons of air resistance acting in the opposite direction. The mass of the car is 750 kilograms. What is the acceleration of the car? Well, firstly, we need to work out the resultant force, because remember, Newton's second law is the resultant force. Resultant force is equal to 300 newtons subtract 150 newtons, which is the same as 150 newtons. So our resultant force, we can then take this and insert it into our formula. So our force is 150, which is equal to 750, because that's the mass, multiplied by the acceleration, which is yet to be found. We don't know this yet. So what we can do is we can rearrange this formula by dividing both sides by 750 to get our acceleration. Our acceleration, therefore, is 0.2. The units for acceleration are meters per second squared, so my final answer is 0.2 meters per second squared. If we look at this car again and say the mass is 800 kilograms, we can work out the acceleration. So F is equal to ma. The force is 800 on this side, subtract 400 from this side. Well, that means the total resultant force is 400 newtons to the right. So we can plug that into our formula. 400 is equal to 800 multiplied by the acceleration. Divide both sides by 800, so we get an acceleration of 0.5 meters per second, or 0.5 meters per second squared. Inertial mass is a measure of how hard it is to change the speed of an object. Inertial mass is defined as the ratio of force over acceleration. You do not need to apply this in a formula, you just need to know what it is. So it's worth learning the definition of inertial mass, as it may come up in the exam. And before we go off and do a task, it's worth noting that this symbol here just means an approximation. It's an approximate answer. So a little squiggly line like that just means approximately, and approximately just means near enough. So if you're following along in your revision workbook, pause the video now and complete task number 8. Next and finally for this video, we're going to look at Newton's third law of motion. Newton's third law of motion states that whenever two objects interact, the forces they exert on each other are equal and opposite. Basically that means that for each force involving two objects, there is an equal force in the opposite direction. So if I pick up an apple, I exert a force on the apple, and this is what makes it accelerate upwards, because we know from Newton's second law that force is causing acceleration. But then the apple also exerts an equal force onto my hands, albeit in the opposite direction. So if I have an apple, let's say this mug is an apple, and I push that apple upwards, well, that apple is also pushing down into my hand with the same force that I'm pushing that apple upwards, or in this case, the mug. So the upwards force is the normal contact force, and the downwards force, well, that's also the normal contact force. Newton's third law of motion can be applied to floating objects which need to be propelled. One example of this is rockets and planes. Rockets propel themselves forwards by thrusting exhaust flow backwards. As this fuel is experiencing a force acting backwards, the rocket experiences a force equal in magnitude but in the opposite direction, i.e. forwards. And this little diagram here shows how that works. So if you have this rocket here and you have this big exhaust here and you've got lots and lots of matter being propelled away from the outside out the back, then what you get is you get a thrust forward. And that's because this stuff coming out of the rocket has to have a force being pushed that way. But there's an equal and opposite force pushing the rocket forward. So upon ejecting this mass from the back, you're pushing that rocket forwards. And that's quite similar to how rockets actually work. Newton's third law of motion, we're going to apply this to a more common situation now. If I have a book and I place it on a table, then the book will not fall through the table. This is because the force of the book on the table is mirrored by the force of the table on the book. The book experiences a force acting upwards, preventing the book from falling through. So if I place this physics book on this table, then the physics book does not fall through the table because the table is providing that physics book with a force upwards, so it doesn't go through the table. If the weight of the book was there and there was no normal contact force, then it would just go through the table, and we know that this simply doesn't happen. If you're following along in your revision workbook, pause the video now and complete task number 9.
Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backroadtutoring.com.